All right, so this is going to be module number 7, and we're going to talk about model complexity. Recall that we were talking about the minimum description length, which allowed us to select the correct, in quotation marks, model, but there are complications. We perhaps, kind of, maybe, in some cases, not always, cheated. So recall that if we have a finite model class capital C, and recall that capital C is a class of possible models. There could be a very finite, very fixed number of models, or more typically, there may be a parametric class, and as the data becomes longer, the number of models increases with the data. But if it's a strictly finite class of models, then the length of a specific model, which we call lowercase c, is well defined. But what if capital C is infinite? What length of C do we have when we have an infinitely large number of possible models? So we need some sort of principle for the complexity of a model. And in particular, we want to understand how the cardinality of the set capital C, the number of models in it, is going to scale with the data size n. So some motivation. How does model complexity relate to data science as a whole? So suppose that you have a specific model, lowercase c, within the model class capital C, and your data has probability PC of x. And as we said before, overall, you're going to try to select the model lowercase c that minimizes the length for x given c and the length for c. Now, I've already mentioned that we're going to see that it's helpful if we have a single parameter to have something on the order of square root of n models. And each is going to have a probability, which is, again, on the order of 1 over square root of n. So 1 over square root of n probability times square root of n models is 1, and the total probability will be 1. That's one of our probability axioms. And therefore, the overall probability for x, assuming that each of these models is assigned the same probability, is going to be PC of x multiplied by 1 over square root of n. So this is the probability for x within a learning framework. So there are a lot of things that you can do with such a probability for x. You could use it for data compression. As I said earlier, there's a two-part scheme where first you compress, you encode into bits the optimal C that you chose, and after that you use the model C to compress the data X. Another possibility is that model selection can be used to perform other statistical inference tasks. Okay, so it's not just data compression, it's not just finding the best model, it also could be find the best model, then use it for classification or clustering or you name it. So what I'm trying to say is that we want to understand more about machine learning approaches and how they may relate to the complexity. So here's an example for a parametric model. Imagine that a student, we have capital N students, and student number n is from 1 to capital N, is either purple or green. And I'm specifically making this up because we all know that students are not purple or green. So this is a completely fictitious example, okay? So once again, I just want to emphasize that n, the index, is a member of the set 1, 2, up to capital N. Capital N is the number of students. And here's an elementary model. Xn, the status of student number n being either purple or green, they're going to be independent and identically distributed, or IID. So independent means that if you have two different xn's, xi and xj, xi and xj are going to be statistically independent of one another. Think of it as you have coin flips. The coin flips might not necessarily be 50-50, but you're flipping a coin for xi, and then you're flipping a coin for xj. And our life experience tells us that if we flip a coin twice, unless we have a very, very special flipping style or we're cheating or something, there's no reason to believe that there's any dependence between these coin tosses. The second part is identically distributed. So if it's a 30-70 coin or 30% purple, 30% green, those probabilities will be in place for x1, for x2, all the way up to xn. Every single student is going to have the same distribution. Okay, so they may be biased coin tosses, but each of them is the same coin, and multiple tosses of the same coin are independent. So we're going to denote the probability of P, purple, as theta, and the probability of G will be 1 minus theta. Again, the total probability is 1, but the parameter theta is unknown, and we'd like to estimate theta. So how are we going to do this? To estimate theta, a simple approach is to count the number of purple and green students empirically, and then you're going to map the probability to the model class. So again, let's think about this. So theta, if I recall correctly, it's the probability of purple, and if that's actually 1 minus theta, let's just go with it. So suppose theta is the probability of purple, and theta hat would be the number of purples divided by the number of purples plus the number of greens. So we counted the number of greens in the data, we counted the number of purples in the data, etc. Now you'll note that the total number of observations, the number of coin tosses, the number of students is n. So number of purples plus number of greens is n. And therefore, we have either number of purples divided by n, or 1 minus the number of greens divided by n. Now, why is that? Because the number of purples divided by n plus the number of greens divided by n is 1. So, okay, so one possibility is that you'll have a finite model class, and if you have a finite model class, you could map to this, or maybe you have a complicated model class, an infinite dimensional model class, all the real values from 0 to 1. So the coding length, the complexity, the length of C for an infinite dimensional model class is not really clear. But we only have an observation, so it doesn't really make sense. So now think about it, that the number of purples, it could be 0, so it's an element of the set that could be 0, could be 1, could be 2, all the way up to n. So there are n plus 1 possibilities. And I'll just abbreviate that by POSS, possibilities. So now, the probability of purple, we denoted it by theta, or rather, theta is the true parameter. And then we said that we have theta hat is the empirical parameter, EMP for empirical, okay? And now let's proceed. Let's define a random variable. Purple will be mapped to 1, green will be mapped to 0, and let's analyze this random variable. So recall the probability space definitions, omega, F, and P. Omega is the set of outcomes for a single student, purple or green. Then we have F, the field. We have the empty set. We have the set omega, purple or green. Then we have the set purple. Then we have the set green. 4 different sets. That's the omega and the F. And the P, of course, is theta, or 1 minus theta, for the case where we have a single coin toss. If you have 2 coin tosses, then you would have 4 different outcomes in omega, and so on. There are different ways how you could define n different coin tosses. But let's look at only xn. Xn is a single random variable. What's its expectation, its average? With probability theta, you have purple. Purple is mapped to the random variable. Its value is 1. With probability, the rest of the time, 1 minus theta, you're mapped to 0, green. 1 times theta plus 0 times something is theta. What about the variance? The variance is the expected value of x of n minus its expected squared. So now let's work through that just a bit more carefully. The variance is the expected of xn minus e of xn squared. This is equal to the expected of xn squared plus the square of the expected of xn minus 2 times xn times e of xn. Now, there's this nice feature of expectation. It's a linear operator. Expectation of three expressions, a plus b plus c, is the expected value of a plus the expected value of b plus the expected value of c, where a is xn squared, b is its expected value of xn squared, and c is the third term. So we have the expected value of xn squared plus the expected value of xn squared minus, and another feature of linearity is that the 2 times can be taken outside the expectation, minus 2 times the expected value of xn times e of xn. Now, the expected value of an expected, e of xn is theta, e of xn squared is theta squared. Theta squared is a constant, and therefore the expected value of that thing squared is theta squared. Next, what's 2 times the expected of xn times something? That something is an expectation. An expectation means that it's a constant, it's theta. So minus 2 times e of xn times e of xn is equal to minus 2 times e of xn times theta, which is equal to, we can take the theta outside the parentheses, minus 2 times theta times e of xn, and e of xn is also theta, so we have minus 2 times theta squared. Finally, the expected value of the square of xn. Think about it. The xn is 1 or 0. The square of xn is 1 squared or 0 squared, which is 1 or 0. 1 occurs with probability theta. 0 occurs with probability 1 minus theta. And for some reason, now I'm getting the capitals. For some reason, I wasn't getting capitals. So overall, the expected value of the square of xn is theta. And finally, combining all these things together, the variance is theta plus theta squared minus 2 times theta squared. The theta square and the minus 2 theta square, they add up to negative theta square. So it's theta minus theta square. Again, I'm having a problem with the capital T. And I can take the theta outside the parentheses, and I multiply it by 1 times theta. And that's the result that we have over here. Now, there's this nice property. If you sum over n students, the expected value of a summation is linear in n, and the variance of the summation also grows linearly. Okay? So we're summing over NIID random variables. Expectation is linear in N. It might be more surprising that the variance is linear in N. I suggest that people think about this, and maybe you can put it on Piazza and discuss. I think that that would be a good exercise on Piazza. And if some of you work through that, of course, Vaibhav and I will be glad to consider extra credit or something like that. Okay, but bottom line, average is theta, variance is theta times 1 minus theta. That's for a single random variable. And when we're taking n random variables, the expectation is linear in n, the variance is linear in n. So now let's think about the optimal, in quotation marks, model class size. The standard deviation is the square root of the variance. And recall that we said that the variance of the summation was n theta 1 minus theta, meaning that the standard deviation, and that was my parrot, of course, is square root of n theta 1 minus theta. Now, temporarily, we can put aside the theta times 1 minus theta. It's a constant. Let's focus on the standard deviation being proportional to square root of n. So now, if you think about what's happening, we have a true probability theta, okay? Theta is going to be the middle of our distribution. The horizontal axis is the empirical distribution. The vertical axis is the histogram, the number of times that it happens. And when we move out one standard deviation to the right or to the left, there's some noticeable but not large reduction in the histogram. Histogram corresponds to a PDF. When we move to 2 standard deviations, that's when there starts being a significant reduction. And 3 standard deviations, that starts being rather uncommon, okay? So now we have the true theta, but the empirical theta, theta hat, is centered around theta. So theta hat is equal to theta plus minus something that's proportional to 1 over square root of n. So now you could think to yourself that even if I know the true theta, with the true theta, anything that's give or take 1 over square root of n away is what we would expect. And the possible range for theta hat is from 0 to 1. And for any true theta, the range of interest will be proportional to 1 over square root of n. So now we can cover the range from 0 to 1 with square root of n, roughly square root of n, proportional to square root of n, order of square root of n, and we'll talk about O notation soon. Order of square root of n parameters will cover the range from 0 to 1, such that each of them will be the amount of the typical type of variation that we would expect around the true theta. So another perspective would be percentages. The number of purples divided by n is theta hat. It's between 0 and 1. The standard deviation proportional to 1 over square root of n, and a possible model class might be multiples of 1 over square root of n. There are better model classes, but the point that I'm trying to convey here is that if the number of parameters is proportional to square root of n, doesn't mean that it needs to be exactly square root of n, but proportional to square root of n, and we take theta hat and we map it to one of these parameters in our model class, the closest one, we're going to have reasonable performance. So a bit about the algorithm and its complexity. Without any information, we have roughly square root of n models for a single parameter in our model class C, and they all have the same probability, proportional to 1 over square root of n. And recall the MDL principle. We optimize for the sum of the length for the data given C and the length for C. And if the length of C is constant, we're just choosing the best length C of X. So if C corresponds to some parameter theta, then what's going to be the length for C, length for X given C? So it's the negative log base 2 of the probability that the model C assigns to the sequence X. Now, what's that probability? So we're going to have number of purple times purple appears with probability theta, and n minus number of purple times green appears with probability 1 minus theta. And this gives us a probability. And the log base 2 or negative log base 2 of that gives us a coding length. So the bottom line is that we're selecting a model class C that maximizes the probability. Maximizing probability minimizes the coding length, assuming that in our parametric class with a single parameter, they all have the same probability, thus they all have the same length. If you would give them slightly different priors, the task would be a bit more complicated, but that's more advanced. Another issue is regularization. We've seen that if we have a single parameter, we need something proportional to square root of n models. But what if we have k parameters? So for example, imagine that we have a probability of being above or below some height for the green students, and another probability of being above or below some height for the purple students. So we have two probabilities. Each of them is a parameter, and we're evaluating both whether a student is green or purple, and we're noting whether they're above or below that height. We're noting down these two binary variables for each of the students, and we now have more parameters. And if we have k parameters, and for each of the k parameters, we need something that's proportional to square root of n parameter values in our model class. And the total size of that space is now, so if you think about it, we have square root of n per parameter. We have k parameters, so n to the power of half k, which is equal to square root of n to the power of k. Now, again, note the order of, so there are going to be constants, and we're proportional to n to the power of half k. Now, what about if that's the total size of the space, so that's the cardinality of C, then what about the coding length? The coding length is the log base 2 of the cardinality, which is half k log n. So there was a famous result by Risanen. I mentioned previous model that he died earlier this year. There was a famous result from 1984 where he showed under various technical conditions and so on that if you have k continuous parameters, in the data compression world, he talked about redundancy. Redundancy is the penalty that you pay for lack of knowledge of the true parameters, the true probabilities. The redundancy is very close to half k log n, otherwise known as half log n per continuous parameter. More generally, regularization penalizes model complexity. So you'll often be regularizing, you'll be assuming that each parameter costs you half log n bits, and then you'll be using that as part of your derivation. You're going to see this, I believe, in homework number 2, which we will likely discuss in class. There are different types of regularizers that could be used. The half log n per parameter is one approach. There are other approaches that can be used. And of course, the literature is complicated. So that's going to be it for this module. And next time we'll be talking about homograph complexity.